We are on Unit 5. This is Notes 1, our first section of Unit 5. Unit 4 was a rather small unit for us, just had a couple of applications of function analysis. This unit, on the other hand, is quite a long unit for us. This is jam-packed with new stuff. And we're going to begin with antiderivatives and indefinite integration. So let me take a look at where we have been, something that we are familiar with. We're all pretty much experts with using the power rule for derivatives, right? So if we were given f of x is, say, 2x cubed, and we were asked to find the derivative of f with respect to x, we would say f prime of x is equal to, and then we would multiply 3 times the 2, and then subtract 1 from the exponent, and so our derivative would be 6x squared. If our function was, let's say, 5x to the negative 4, the derivative would be negative 4 times 5, x to the, we would subtract 1 from the exponent, negative 5, right? If we had, let's say, f of x is 9x, asked to find the derivative, f prime of x would be, we know the derivative of 9x is just 9. We can think of that as multiplying 1 times 9, getting 9, and then subtracting 1 from the exponent, and the exponent would be 0, and x to the 0 is just 1, right? So this was all using the power rule for derivatives. And we got very comfortable using power rule for derivatives. We could do it with negatives, we could do it with fractions, different things. So power rule for derivatives, that was a nice one for us. Okay, now in this first section, we're going to be going backwards. So I'm going to give you the derivative. What if I gave you this derivative? The derivative is 6x squared. How can we get back to the function? Okay, so if I give you the derivative, what is the function? Okay, for this process, we don't call it as finding a derivative. We want the function whose derivative is this, so we're actually finding the antiderivative. The antiderivative of this function. What is it? Okay? So that's what we're doing. So what would you do in general? I know the answer is sitting there looking at us, but what would you do? Well, to take the derivative, you subtract 1 from the exponent, right? So for an antiderivative, we must have to add 1 to that exponent, correct? Now we're looking at this function. To take the derivative of this function, we would have to multiply 3 times whatever used to be here, or multiply 3 times whatever is there to get 6. So 3 times what is 6? Well, 3 times 2 is 6, right? So let's see if I can color code this. We got that 3 by adding 1 to our old exponent. Now what can we say, how can we get 2? Well, we can take this 2 by dividing our old coefficient by our new exponent, right? That would be 6 divided by 3. So add 1 to your exponent, divide your coefficient by your new exponent. Let's see if it works for something else. Let me give you this one. How about if we have f prime is 4x cubed? Okay. What is f? What is the antiderivative? Okay. All right. Begin by adding 1 to your exponent. Add 1 to your exponent. And then think, what do we multiply 4 by to get 4? What do you multiply 4 by to get 4? Well, it has to be a 1, right? So the 4 is gotten by adding 1 to your old exponent. the 1 we got by dividing our old coefficient by our new exponent. Okay? Let's do another. What if we have 5x? F prime is 5x. What is f? Whose derivative is 5x, right? So begin by adding 1 to your exponent. Well, our old exponent is 1, so our new exponent must be 2. What do you multiply 2 by to get 5? What do you multiply 2 by to get 5? Well, it has to be 5 over 2, because we multiply 5 halves times 2 and we get 5. Okay? So again, that worked. Add 1 to your old exponent, divide your old coefficient by your new exponent. 1 plus 1, okay, by your new exponent. Alrighty. Okay, so now we kind of are developing something here. If I have f prime is 3x squared, and then I would say f of x, the antiderivative of 3x squared would be x cubed, right? And then divide 3, the old coefficient, by our new exponent, and we would get 1, right? So we would have f of x is equal to x cubed. And if we went backwards, if we applied our old friend, just our power rule for derivatives, we would get 3x squared, and that matches, right? Matches. So you can always check this by taking the derivative and see if you get back what you should get back. Okay. Now my question is this: is x cubed the only function? So this is an antiderivative for sure. X cubed is an antiderivative of 3x squared. My question is there anything else whose derivative would give us 3x squared? What if we had x cubed plus 1? What's the derivative of x cubed plus 1? 3x squared plus 0, because the derivative of 1 is 0. So once again, we got the same function that we started with, right? What if we had x cubed plus some other constant, like pi? What's the derivative of that? 3x squared plus, what's the derivative of pi? 0. It's just a constant, right? So once again, we got back there. So as long as we have x cubed plus some constant, we will get our original function. Okay, so each of these is an antiderivative of 3x squared. Each of these is an antiderivative. If we're asked to find a general expression for the antiderivative, then we would go with this one right here. C is any constant. All right? Okay, a word about notation. Before I do that, let me come over off to the side here. What if we had f prime of x is x to the negative 1? In fact, let's make it 2x to the negative 1. Let's try to find the antiderivative here. Okay? The antiderivative. So we add 1 to our exponent, correct? Add 1 to our exponent. Negative 1 plus 1 is 0. And then we divide our old coefficient by our new exponent. What's wrong with that? Well, what's wrong with that is that's an undefined value. This rule, this process that we've developed, only applies only applies if this exponent is not -1, okay? If it is -1, let's go back just to plain old x to the -1, okay? If it is a -1, let's think about that. That means 1 over x, right? We already know a function whose derivative is 1 over x. What function's derivative is 1 over x? Well, yeah, it's ln of x. That's ln of x. Now, x, though, in this function, in this antiderivative, we're assuming that x can be anything, right? Positive, negative, it's any real number, correct? Can x be any real number here? No, because our argument has got to be positive in a natural log. So we're going from a domain of all real numbers. For this, though, we have got to restrict it. So we've got to make that an absolute value, okay? Plus constant. So always remember, we're finding the antiderivative. We're finding a function whose derivative is this function, okay? So what we developed is called the power rule for integrals. And that brings me to a little notation. Our notation for an antiderivative, okay? We denote the antiderivative of f of x as this. That's our notation for the antiderivative. So that's where we would be putting like 3x squared. So we can say the antiderivative of 3x squared dx is x cubed times 3 over 3 plus c. Okay? So this is our notation. This means antiderivative. So that's the antiderivative of that. Okay? What's the dx for? Well, the dx tells you which variable to integrate with respect to, which variable to find the antiderivative with respect to, okay? And it is very important, and we'll see more why that's important coming up in our next section. I believe, or maybe even the following section, but it's coming up soon, all right? But this is important. Never write this symbol. This symbol, it looks like a long, skinny S, doesn't it? It actually stands for sum, which again, we're going to get to in our next section, all right? But it's a long, skinny S. Leibniz is the one who gave us this, okay, this notation, but it came from a summation. So just know that that is, it looks like an S and it is an S. It means S, it means sum, all right? But this dx is vital to this notation, okay? It tells you what variable to integrate with respect to. In Calc 1 and Calc 2, we'll only have one variable here. But in Calc 3, you'll have 2 and 3 variables here. And theoretically, you can have as many as you want. So this is vital. This tells you what variable you're integrating with respect to. Okay? All right. So we have developed what is known as the power rule for integrals. And essentially what it does is it undoes the power rule for derivatives. Okay, it's what we've just been developing here. Okay, so the power rule for derivatives says if n is any real number, if n is any real number except negative 1. Because remember, it doesn't work if that exponent, n is going to be our exponent, so it doesn't, the power rule for integrals does not work if the exponent is a negative 1. Okay? If n is any real number except negative 1, then, okay, the antiderivative of x to the n dx with respect to x is equal to, okay, take x, take the exponent, right? Take the exponent, add 1 to the exponent, and then we're, in this case there's a 1 out in front, we need to divide that 1 by n plus 1, right? So I can write this two ways. I could write it all over n plus 1. I could do that, plus c. I could do that. Or another way to write that, and we do both of these, is raise that exponent by 1 and then do 1 divided by n plus 1 plus the constant of integration. Okay? So both of these, of course, mean exactly the same thing, right? And like I said, I kind of, you'll see me more use it as a fraction in front of that x, but they're exactly the same meaning, so it doesn't matter. C is called the constant of integration. Okay? All right. So I would read this as the antiderivative of x to the n dx, or the antiderivative of x to the n with respect to x is equal to x to the n plus 1 over n plus 1 plus c. Okay? All right. So that's our power rule for integrals. And I will tell you that we don't just have a whole lot of rules for integrals, okay? Unfortunately, there is no product rule for integrals. There's no quotient rule for integrals. There's something that we think of as the chain rule for integrals. It's not really called the chain rule, but it is very similar to the chain rule. We call it U sub, but anyway, we will get there soon as well. Okay, but the power rule for integrals is our go-to. Almost everything we have to bring back to this form. Okay, so this is big for us. All right, now, of course, it doesn't work for everything. For instance, what if I needed the antiderivative of cosine x? What if I needed the antiderivative of cosine x? So remember, we want a function whose derivative is cosine x. Well, what function's derivative is cosine x? Sine x plus c plus any constant, right? You can always check it. What's the derivative of sine? Cosine x plus this, the derivative of c would be 0. So the derivative of this would be cosine x. What we got? Okay. What about the antiderivative of sine x? Antiderivative of sine x. Well, what function's derivative is sine x? Negative cosine x, right? If we took the derivative of negative cosine x, we would get sine x. Okay? What about the antiderivative of secant squared x? Which function's derivative is secant squared? Well, that's tangent. Okay? let's go off to the side. What function's derivative is cosecant squared then? That would need to be negative cotangent x plus c. So the antiderivative of cosecant squared x dx is negative cotangent x plus c, because we can have any constant added and still get back that derivative. Okay, in the last one that we will have here is secant x tangent x. Well, not the last one, but you know what I mean. The last one that we need to kind of put a little thought into. So, what function's derivative is secant x tangent x? That is secant x plus c. And then what function's derivative is cosecant x, that's an s. Let me redo that. Cosecant x cotangent x dx. That would be a negative cosecant x plus c. Okay? So you need to know these. You need to know these. And, I mean, it's just knowing the derivatives. If you know the derivatives, then you'll know the antiderivatives of these. It's not that hard, right? If you know the derivatives, it's easy to get the antiderivatives. It's like, here's the answer. What function was it? What function's derivative is secant squared? So, yeah, that's all there is to it. Okay? Not too bad. Okay, let's take a look at some examples. And by the way, you'll hear me use the term integration as well as antiderivative. Those mean the same thing. Okay, if I have the antiderivative of f of x dx, I read that in two different ways. I read that as the antiderivative of f of x dx, or with respect to x, or dx. Okay? Or I can read that as the integral of f of x with respect to x, or dx. Two ways to read it. They mean exactly the same thing. So antiderivative is integral. Okay? Sound good? Doing great, doing great. Let's look at some examples. So example 1. Let's find the antiderivative of 8x cubed minus 9x squared plus 4 with respect to x dx. Okay? Well, this would be go term by term, right? Just like we did with derivatives, we were able to go term by term, yeah? So we're going to be doing the same thing with integrals or antiderivatives. So for this first term, add 1 to your power and then divide by that new power. So 8 divided by 4 is 2. The sign will stay the same here. Add 1 to your power and divide by your new power. So 9 divided by 3 is 3. What about the antiderivative of 4? Well, what function's derivative is 4? That would be a 4x, right? So the antiderivative of 4 is 4x plus c. If you don't put the plus c, all right, if you don't put the plus c, then you have found one antiderivative. You just have not found them all. By putting the plus c, we're going from a single antiderivative to an entire family of antiderivatives. Okay? So essentially, if you don't put the plus c, you got one out of an infinite right. Okay, so always put your plus c, all right, if you're finding an antiderivative. Okay, All right, number 2, the antiderivative of the third root of x squared plus 1 dx. Okay. All right, this is equal to, well, I need to at least think of this cube root of x squared as x to some power, right? That's what we did with derivatives. So I'm going to come off to the side real quick here and make that x to the, okay, what is that? X to the what? So think about it. Think about what you would tell me if we were in class. All right. The 2 here stays on top. The root goes on the bottom. Root is always on the bottom, right? Okay. And by the way, this is a good time to bring this up. The problems will almost always have these parentheses to start with in here if there's more than one term, okay? And that's fine to keep them, but you don't have to keep them. That's another thing that this dx does. The dx closes your integral, okay? So you can write the parentheses or you don't have to. But either way, you always have to have the dx there, or d whatever your variable is. Okay? All right, so now let's apply the power rules. So we're adding 1, add 1 to your exponent. 2/3 plus 1 is 5/3. And then we're doing 1 divided by 5/3, right? Well, what is 1 divided by 5/3, you guys? Yeah, we flip that. This will be 3/5, okay? Plus, what's the antiderivative of 1 with respect to x? This is another thing. If there's just a number here, you need to know what letter to put there, and this tells you what letter to put if there's just a constant here. The antiderivative has to have an x with it, right? So x plus c. This would be a safe stop spot, but these will all be multiple choice. So this will be 3/5 x to the 5/3 plus x plus c. That would be the MC answer. Okay. Number 3. What about if we have 3 divided by x to the 7th? 3 divided by x to the 7th. Okay, well, first of all, rewrite that as 3x to some power. Because remember the power rule, where's my power rule? The power rule only works if it's x to a power, not 1 over x to some power. No, it has to be x to some power. So you always have to at least think of this as x to some power. Right now it's not x to some power, it's 3 divided by x to some power. So be careful with that, okay? So this will be, add 1 to your power, -7 plus 1 is -6, not -8. And then we take this old coefficient and divide by our new power, right? So this would be -1/2 x to the -6th plus c. That might be the multiple choice answer, or they might move that x to the -6 to the bottom and make it a positive exponent. And that might be the multiple choice answer. But one of these would be the multiple choice answer. Okay? All right, number 4. What if we have this? 4t squared plus 3 all squared. All squared. Okay. Does it matter if there's this big square out here? Yeah, sure it does. We can't just go in here and use the power rule for integrals inside and then square it. That's not how it works. That's what I was saying. This is really our go-to. So this is kind of all we've got. It's all we've got. So if you have x plus 3 to the 7th, you can't use the power rule immediately. What do you have to do? Well, we have to go ahead and, well, first of all, these need to be matching. So I'm going to put a t there. I didn't see that. I just wrote it wrong. If there's a t here, then for us this year, there's going to be a t here, right? It's not going to, they're going to match. In Calc 3, they might not match, so you'll have to be careful about that. But for us, those are going to match, unless Mrs. Murray had a little typo. All right, so we have to go ahead and multiply this out, square this binomial. So when we square the binomial, we'll have 16t to the 4th plus double the product, right? Double the product, so 24t squared plus the square of the last. And now it's just power rule, okay? So always get it to where you can use the power rule. It's all we have. So that's all you can do. So just power rule, power rule, power rule. That's all you can do. Okay, so this will be t to the 5. And then here we'll have 16 over 5, right? Plus t cubed 24 over 3 plus, don't forget we're integrating with respect to t now, so this will be 9t plus c. Okay? What about this one? Let's change our variables again. Theta squared plus secant squared theta d theta. Okay? So our variable is theta here, right? Well, you can always think of it with x's. If you don't like the thetas, doesn't bother me if you change it all to x's, okay? You certainly don't have to, and I wouldn't, but some of you are like, oh no, I don't do thetas. Well, no, I don't care. Change it to x then. But just be sure that you change every theta to x, not just the ones that you want, okay? All right, but I'm going to keep our thetas. So theta is our variable. So this would be theta cubed, right, times 1 over 3 plus, okay, what function's derivative is secant squared theta? What function's derivative is secant squared theta? Well, that's our tangent theta. The derivative of tangent theta is secant squared theta plus c. Okay? By the way, if you do choose to use x's, you got to go back to thetas at the end. All right? If it's a multiple choice, you got to go back to thetas at the end. Okay? All right. Just a couple more here. What if we have this? What if we have 4x to the 5th plus 2x to the 4th minus x squared all divided by x squared? Okay, I already told you there's no quotient rule for integrals. Can't do it. Can't do it. The only thing we have is the power rule for integrals. It's all we've got. Unless it's one of these where we know the antiderivative. Okay? That's all we have is the power rule, so you've got to put this into a form where it's x to some power, plus x to some power, plus x to some power. That's all we can do. All right? So here, I'm going to use what I know about this kind of function, and I'm going to divide every term on top by this x squared. So this is the same thing. You would not write this out, but this is the same thing as this. Isn't that? If you were given this back in Algebra 2 or something, well, there's our common denominator. So there's our common denominator, and then you just add up everything on top, right? Well, this is just going backwards. We're just breaking it down. Here we're breaking it down rather than putting it all together. Okay? So this would be the antiderivative of 4x cubed plus 2x squared minus 1. Right? And now it's power rule. So you're always getting it to the power rule form. Okay? So power rule. This will be x to the 4th. 4 divided by 4 is 1. Plus x cubed. 2 divided by 3, 2/3. Minus x plus c. And you can always go backwards. You can always take the derivative and make sure you get back where you started. Okay? All right. Couple more little examples. In this example, we have some different directions. It says solve the differential equation. I always get excited the very first time that I write this each year. Solve the differential equation. Because we've never solved a differential equation yet, and this is our first one, and that's really kind of cool. Given that f of -1 is 3. Okay. So yeah, there's an entire course in college called differential equations. Okay. If you're going into engineering, you will very likely be taking that class. Okay. If you're doing computer science or something, then you may not have to take it. But anyway, it's devoted to that. But in this class, we do some very basic called separable differential equations. But anyway, let's solve this differential equation. So the first thing is, what the heck does it mean to solve a differential equation? Okay. Well, solving a differential equation, you're going to hear that. You're going to hear me say it all year long. Solving the differential equation means finding the finding the function that meets all the criteria in the problem. That meets all given criteria. Essentially. Okay. The criteria will involve a derivative. That's why it's called differential equation. It's differential because the equation has a derivative in it. Okay. When we're going to solve the differential equation means we're finding the function, essentially, whose derivative is this, and who meets any subsequent criteria. Okay. So we start with what we're given. We know that f prime of x is 4x squared. Okay. Now I'd like you to start to think of this, and I know we could do what we did when I first sat down with you here in this section. We could just find the function. Okay, I get that. I'd like you to start thinking of this as what you're doing to one side, you're doing to the other kind of thing. Okay, so here we have f prime of x on one side, 4x squared on the other side, right? And an equal to in between them. Well, what are we really doing on both sides? We are actually taking the integral of both sides, right? We're integrating both sides with respect to x in this case. Okay? And when you integrate f prime, you get back f. It makes sense. The antiderivative of the derivative of f is f, right? Yeah? Okay. And that's equal to x cubed times 4 over 3 plus c, right? Okay, so we've satisfied the very first part because f prime is 4x squared. Now we need to satisfy this part. F of -1 is 3. Right now, I don't know. What is f of -1? Well, f of -1, we need that to be 3, right? Well, that's f of -1. We need that to be 3, correct? This will allow us to find the single constant that satisfies both of these. It'll make our function satisfy both of these. Okay? So this is negative 4/3, right? So C will be 3 plus 4/3, which 3 is 9/3, and 9/3 plus 4/3 is 13/3. Okay? So what is our answer? We're supposed to solve the differential equation, which means finding the function. What is our answer? Is our answer 13/3? Is that the function? No, it's not the function. Our function is 4/3 x cubed plus 13/3. Your answer is the function, not just the constant variable, the value of the constant, okay? I stress that because I don't know how many times I've graded papers, you guys, and you're asked to solve a differential equation, and kids find C down here, and they box C and call it a day. And that's not correct, of course, because the answer will be the function with that value of C. It's with that value of C. So this function, when we take the derivative, we get 4x squared, and it also satisfies that condition. This is called an initial condition. Okay? All right. What about this one? Let's solve this differential equation. Solve the differential equation, and I will start abbreviating differential equation because it's quite a bit to write. Diff EQ. That means differential equation, all right? Solve the differential equation. F double prime of x is equal to sine x. Given that f prime of 0 is 1 and f of 0 is 6. So now we have several criteria. We're finding a function that meets all of these, right? Start with your differential equation that they give you. So start with the f double prime. So I have f double prime of x, I'm leaving myself a space because I know what I'm about to do, is equal to sine x, right? We're going to integrate both sides with respect to x. Integrate both sides with respect to x. Well, the integral of f double prime would be what? That would be f prime, right? The integral of f double prime would be f prime. The antiderivative of f double prime would be f prime. Okay? What's the antiderivative of sine x? What function's derivative is sine x? Negative cosine x, right? Plus c. Now we need to find this c. Before we go on, before you go on to find f, go ahead and find the c. Alright, so f prime of 0 is equal to negative cosine of 0. Well, cosine of 0 is 1, so that's negative 1 plus c. But I know that that is equal to 1, right? So c must be 2. So f prime of x is negative cosine x plus 2, right? Now we need to keep going because we haven't found the function yet. We've found the derivative of the function, but we haven't found the function. So now we do the same thing again. Leaving myself a little space. Okay, we integrate both sides with respect to x. The antiderivative of f prime is f. Okay, What function's derivative would be a negative cosine x? That would have to be a negative sine x, right? The derivative of sine is cosine, and then we would need a negative there, right? Okay, plus 2x plus c. And now the last thing we have to do is find this c, this constant. All right, so f of 0, sine of 0 is 0, 2 times 0 is 0, so this ends up just being c, and I know that that has to be a 6, so c has to be 6. So our function is negative sine x plus 2x plus 6. So this function has second derivative sine x, f prime of 0 is 1, and f of 0 is 6. Alrighty. Big concepts in here today. One of my favorite sections, definitely. Anyway, good deal. Go try your homework and let me know your questions.